I welcome you all for the module 3 lecture 1. Now, we will have a overview of the module 3 in which we will be discussing about limits, fits and tolerances. Now, we will discuss about what are the reasons for size variations during manufacturing and what is the meaning of manufacturing tolerance and fit, and what are the limits of work parts like upper limit and lower limit, and then what are the various considerations in allocating the tolerances for the work pieces. We will also learn about the some of the related standards, and we will discuss about the various types of tolerances, system of fits, and what are the various kinds of types of fits, and then what is the meaning of international tolerance grade, and what is the necessity of tolerance grade, and how do we select the kind of fit that is required depending upon the application, and then what are the various geometrical tolerances, and then we will also learn about the positional tolerances, and then we will move to the limit gauging part of the lecture, wherein we will be studying about the meaning of gauging and necessity of gauging, and how the gauges are classified, how they are manufactured, and what are the various types of gauges that are available for the gauging purpose. And then we will also learn about the Taylor's principle of gauge design, and what is the gauge maker's tolerance and what is wear allowance, and then we will have some numerical problems. Now, we will start the first lecture, the product design considerations. Whenever a new product is developed, the various considerations are given for the development, design and development of the product. So, the engineer will look for the functional aspects of the product, what is the size of the product, what are the various applications of the product, what are the various features the product should have, what is the weight and what is the basic requirement of the customer. All those things one should study in detail. And then what about the durability and dependability of the product. See, when the customer purchases the product, he is worried about the reliability of the product and durability, life of the product should exist for a certain period of time. And then the economical aspects of the product, the customer wishes to purchase a good quality material at very economical prices. So, while designing the product, the design engineer should see how the product can be manufactured more economically. And then there is a relationship between design department and manufacturing department. They will have to sit together and decide about the design and production aspects of the product. And then they have the aesthetic part of the product. The workpiece or the product should be pleasing, should have a pleasing appearance, the color of the product and the shape of the product. These are very important aspects which will attract the customers. And then how it can be marketed, what about the packaging of the product, and those things also one should study. And it is very important that the product should be always eco-friendly, should not affect the environment, it should not spoil the environment. Such things also one should consider. And once the period of the life of the product is over, how it can be disposed, in what way it can be easily disposed without affecting the environment. So, these are some of the considerations while designing the product. Now, once the product the design is made and specifications are fixed and the part drawings are prepared, all the requirements are built into the drawing of the various parts, and that is supplied to the manufacturing department. So, in the drawing the sizes of various parts are mentioned, Now we know that it is always very difficult to produce the parts to an exact size. So when we try to produce the parts to exact size, we have to use more precise manufacturing processes like grinding process or lapping process or super finishing process. So thereby the cost of the product will increase. So we should always see what is the functional aspect of the product and manufacturing aspect of the product, and then we should fix up the what is the allowable deviation. So in order to produce the part more economically, some variation in dimension is allowed by the design engineer, which will satisfy the functional requirement. So the tolerances on mating parts decides the type of fit. For example, so the design engineer has made some calculations, and the design shows that the size of the shaft is 10 millimeter. Now we know that it is very difficult to produce the shaft exactly to 10 millimeter. So he will allow some variation in the dimension, say the shaft can vary within this size, say 0.1 mm. That means the shaft can have the lower limit of lower limit of 9.9 mm, and the upper limit can go up to 10 h limit, higher limit can go up to 10.1 mm. So these are the limits of the work pieces. If the workpiece that is produced is having any size between this 10.1 millimeter and 9.9 millimeter, then it will be acceptable. So now while specifying the tolerances, we should see what is the functional need of the workpiece. This is very important. For example, say we have a hydraulic cylinder like this, wherein there is some pressurized fluid is there, and it is acting there is some pressure, and now because of this we get a force here which can be used to move some load. Now the design engineer should see what is the functionality of this particular product, and accordingly he should decide about the tolerance on the shaft as well as tolerance on the hole. If the clearance between these two is more, then the fluid will leak, and then the required amount of force we may not get. If it is too tight, then the piston may get jammed in the cylinder. So such aspects we should always see before assigning the tolerance values, and then the tolerance that is allowed will definitely affect the manufacturing processes and sequences. If you can see this picture, this is the workpiece tolerance. It will have some effects on the manufacturing aspects. It will affect the cost of the precision. If the tolerance is very tight, for example, instead of 0.2 he specifies 0.002 millimeter, then the manufacturing section has to select very good or precise machine tools like grinding machine or lapping machine, thereby the cost of the product will increase. And if it is loose but it satisfies the functional needs, then we can go for some processes like fine turning or some rough grinding. So it will reduce the cost of the workpiece, and then workpiece tolerance will affect what is the process that is to be selected depending upon the whether it is tight tolerance or loose tolerance, we can select whether turning is okay or fine graining is okay or lapping is okay, so like that. And it also affects ease of assembly. If the tolerances are very tight, then assembly time required will be more. If it is loose, it can be very easily fitted, so that the assembly time will reduce. And what is the effect on the performance? It will definitely affect, as we saw in this particular case. So before the tolerances are assigned, it is very essential that the functional needs as well as the manufacturing aspects should be considered. And then if we provide the proper tolerance on the workpieces, then it will we can have the interchangeability concept, and it will the parts the replacement of the part becomes very easy, since they are available, the workpieces are available in the market, which are produced using the system of fits and tolerances. So the in case the work parts fail, we can easily get them from the market and we can fit them, and the maintenance of the machine tools becomes replacement of the parts becomes very easy. Now we learnt about the tolerances, and now we will see why tolerances are specified. Now if you see this diagram, we have the production system, wherein we have various inputs like the human resource, and then machine tools, cutting tools, and then various measuring instruments, etc., the raw material. So these are some of the inputs, and then finally all the inputs are used in a proper way, and then we get the output. And on the production system, always there will be definitely the environment will affect. Now ideal conditions demand for parts without any kind of dimensional variation, but in actual practice we know that it is very impossible due to the following reasons. The reasons are variations in the properties of the material being machined. For example, the metallurgical property may vary from one place to another place in the raw material. At some places it may be very soft, at some places it may be very hard, and the thermal property of the workpiece also affects the dimensions. And then the production machines themselves will have some inherent inaccuracies built into them. So because of these inaccuracies, the workpieces produced, the size of the workpiece produced will vary, and then it is impossible for an operator to make perfect settings, like the setting of the cutting tool, setting of the machine tool, and then we may always make some mistakes while setting the tools. Because of that, the inaccuracy in the workpiece is introduced. Also the environment, working environment will definitely affect the manufacturing process. The temperature prevailing at the manufacturing site, or the humidity. Because of this the dimensional variations will occur. So because of that, the size of the workpiece will vary. Now there are we discussed about some of the reasons why the tolerances are specified, and we will discuss about some of these points in detail. The influence of geometric accuracy of machine tools on workpiece accuracy. The manufacturer, you can see this picture here, the machine tool will have some inherent inaccuracy, like the movement of the spindle. It may not be perpendicular to the table. For example, so this is the movement of the spindle, and this is the work table, machine tool table. And now this may not be perpendicular, there will be some error, maybe a few seconds or few degrees. Because of that, the geometry of the workpiece will be affected. Also the movement of the spindle may not be perpendicular to the table. Also maybe there are some run out of the spindle is there, and then the axis, I can see in this diagram, the axis of the spindle and then the axis of the tailstock, they are not in line. So there is some inaccuracy. Because of this, there will be some inaccuracy in the workpieces produce. We may get the drum shape of the workpiece, or we may get the taper in the workpiece which are unwanted. So, spindle rotation accuracy plays a major role, and then parallelism of saddle movement of the lathe axis. For example, so we have the saddle and we have the guideway, and then we have the spindle of lathe spindle axis. So, the movement of the saddle may not be parallel to the spindle axis. Because of that, we may get various kinds of inaccuracies in the workpiece, and dimensions also will vary. And what about the straightness of the guideway? This lathe guideway may not be straight, so it may be having some inaccuracies like this. So, because of that also the workpiece will be affected. And then squareness of spindle axis with the table surface, that is what we discussed in this particular diagram. Then because of deflection of the workpiece also, the inaccuracy in the workpiece is introduced. Now because of the self weight of the workpiece, now we can see it has some sag is there in the workpiece. When this is the ideal machining when there is no bending of the workpiece, but actually when it bends like this and when we take the cut, once the workpiece is removed from the machine tool, you may get a shape like this. Also, because of the cutting forces, the workpiece may deflate. Say we have a very thin workpiece like this, and when we force when you press the cutting tool in this direction, because of this force it may deflect like this. So, then also we get some inaccuracy in the workpiece. And the force vibration and chatter, because of the tool chatter, tool vibration, the surface finish of the workpiece is affected as shown here. Now the tool deflection will also cause the geometrical variation of the workpiece and dimensional variation of the workpiece. You can see here there is a force acting at the tip of the tool, because of that the tool is bent like this. So, because of this we may get some rough surface or dimensional changes as shown in this particular diagram, and the tool wear also will affect the workpiece. The various kinds of tool wear, the flank wear or the chipping of the edge of the cutting tool, and then the plastic deformation of the tool tip because of the high temperatures developed, and then the thermal cracks developed in the tool. All these factors will affect the dimensional variations and geometry variations of the workpiece. And then error due to location in fixtures. When the workpieces are mounted in the machine tool, sometimes the jigs and fixtures are used. Maybe the operator has not selected the proper fixture, or he may, while putting the workpiece in the fixture, he may not put them properly. So, because of that the dimensional changes may occur. And then error due to clamping of the workpieces. Now, we can see here we have the table, machine tool table, on which two parallel plates are placed here, and then the workpiece is placed. This is the workpiece. Now, and then using clamps, the workpiece is clamped. Now, sometimes the operator may place the parallel plates like this, and then when the clamping force is applied, the workpiece will bend like this, and now the cutter will cut the workpiece like this, and then once the clamps are removed, the workpiece will spring back, and we get the inaccuracy in the workpiece. Also, because of the slideway friction, the movement of the tool will not be proper, there will be jerky motion. So, because of that the surface finish may get affected, or sometimes the geometry is affected. Now, this is the error due to alignment error. The spindle axis the cutting tool is not perpendicular to the surface. So, because of that there is some error in the workpiece. Also the structural deformation due to varying load, the cutting forces will be acting on the structure, the column of the machine tool. Because of that the column may deflect. So, due to this also the workpiece size variation will occur. And then we have thermal deformation due to heat generation. Now, these workpieces they are subjected to expansion and contraction due to the heat that is generated during machining process. So, because of this variation in temperature, the workpiece will be subjected to, it may expand because of the higher temperature. Now, you can take the example of a workpiece, and then some milling operation is performed on the surface, and then after that immediately the operator goes for drilling of 2 holes like this. Now, because of the milling the workpiece is in a heated condition, and immediately it goes for the drilling operation. So, he puts the drill and there is some tolerance for the center distance. Now, once the drilling is over the workpiece is removed, and then when it cools this because of the contraction the center distance may change. So, like this the dimensional changes will occur, and also the vibration from other machine tools or other operations. For example, in the next room maybe there is some pressing operation is going on. So, because of that the vibrations are introduced. So, the tool may vibrate and it will affect the geometry of the workpiece, and also the reaction forces acting on the various members of the machine tool will lead to deflection of the machine tool, and the errors are introduced. Now, in case of NC machines the input interpolation errors will be there. Because of that there will be staircase effect on the workpiece like this. If we observe this picture, here we can see there is some staircase effect. Okay. So, now other reasons for dimensional changes is servo system errors like dead zone effect and feed drive stiffness, positioning errors of the drives, and then thermal drift is primarily caused by feed axis on the basis of recirculating ball screw. See, because of the movement of the ball screw the heat is generated, and because of that the screw may expand or it may contract due to thermal changes. So, that will because of that also there will be changes in the dimensions of the workpiece. Now, any attempt made to overcome the factors discussed with a view to obtain ideal conditions, that is ideal dimensions, will lead to very excessive cost. So, the part should therefore be made as inaccurate as tolerable to satisfy the functional requirements. Thus, tolerances are specified to the dimensions of all manufactured parts, and these should be just enough to do the intended job. Unnecessary tight tolerances should not be specified. Say, for example, plus or minus 0.0002 mm should not be specified when plus or minus 0.002 mm will satisfy the need. And then tolerance, we should understand that the tolerance is a compromise between accuracy required for proper functioning and ability to economically produce this work to produce the accuracy. We should always understand that while specifying the tolerance the need should be satisfied, as well as we should consider the manufacturing aspect, so that the product can be produced at economical with economy. Now, we should understand that when the dimensions are specified, there are some functional dimensions and there are some non-functional dimensions. If you see this diagram, there are some dimensions like NF are non-functional dimensions. You can see here, this is the outer surface of this particular curved part, wherein no mating part will come in contact at this place. So, at this place we need not have to specify very stringent tolerances. Open tolerances will be alright. In some places like say here F is the functional dimensions, wherein we have a bore in which some shaft will come and it may rotate in the bore or it may slide in the bore. In such cases we have to specify the tolerances with taking lot of care. Now let us try to understand what is the meaning of fit and what is the task of fitting the mating parts. So we can see here we have a bore hole here, we have a part wherein there is a hole and then we have a bush and then there is a shaft. We have to assemble all these three parts. Now we should understand that the bush will be in contact with the body of this particular bearing, and there should not be any rotation or movement between bush and the body. So there the no motion is no sliding or rotation is required. So these two, bush and body, should be held tight, and then here we have a shaft which will be rotating in the bush or it may be sliding in the bush. So there some clearance is required so that it easily runs or it slides. So in such cases carefully we should assign the tolerances. In the olden days such kinds of work were done by the operators called fitters manually. They used to take the shaft and they used to take the mating part that is whole, and they used to adjust the size by using scraping or filing operations or some lap tools. So manually the fitting of the jobs was made. It was very slow and it was applicable only for one-off situations. Now with the advent of the high speed machine tools and the interchangeable manufacture, parts are machined in a very precise and repeatable way that they require no individual fitting, manual fitting of the parts. Mating parts could be taken randomly and assembled to get any required fit. This is possible by the use of proper tolerancing and by use of proper fits and tolerances. Depending upon the fit that is needed, proper tolerance or proper deviation in the size is allowed. Now one of the most important considerations when applying tolerance is the fit. What is the kind of fit? I gave the example of the bush shaft and the body. So between body and bush no movement is required, so there the tight fit is required, whereas between the shaft and bush some clearance is required so that the shaft moves easily. So their clearance fit is required. Now depending upon the application, sometimes clearance fit is also used to allow the expansion due to heat, due to continuous usage of the work part, for example sliding shaft or the running shaft. There will be increase in the temperature, because of that shaft may expand, and if sufficient space is not available, so it may get jammed in the hole. So to allow for expansion also some clearance is allowed, and then what is a sliding fit for better positioning is used, and sometimes interference fit is used for holding the parts together. Now another consideration while allowing or specifying the tolerance is the tolerance stack. Now the design engineer should understand what is the effect of this tolerance stack. We can see here we have three pictures wherein we have four circular features are there with varying diameters, and they have the varying lengths with some tolerances. Now if the tolerance is specified like this as shown in this diagram, okay. Now between the size between the surface B and surface D, okay, the tolerance between surfaces B and D can be as large as plus or minus 0.15 if the specification is like this, and if the specification of tolerance is like this, okay, then the tolerance can be as low as plus or minus 0.05. So this the design engineer should understand, and he should carefully assign the tolerances. Now another important point to be considered is whether the tolerance is specified on radius or diameter. Now in this picture you can see the tolerance is provided on the radius. So 250 plus or minus plus 0.001 mm minus 0. Now in this diagram the tolerance is provided on the diameter, that is 500 plus 0.001 mm, and lower limit is 500 mm. So depending upon whether it is placed on radius or diameter, the diameter will vary. A tolerance on a radius might be looser than proposed, while the tolerance on the diameter might be tighter than planned. Should be considered carefully. And then whether any plating or finishing operation is specified on the surface. So whether plating is required, what is the thickness of the plating, that also should be specified, whether the dimension specified in the drawing is before plating or finishing operation or after finishing and plating. So such things one should consider. And then sometimes the minimum or maximum limits are specified on the drawings. We can see here we have a work part like this, and we have a fillet here, and the radius of the fillet is 0.015 minimum. Now if we follow this, the operator may produce a part with a radius of 0.125 millimeter. So as per the specification this work this size is allowed, but whether it affects the functionality, that we should consider. So we should be careful while specifying minimum or maximum limits. The functionality we should consider. Now sometimes compound tolerances are used. You can see here we have a work part with this particular shape, wherein there is a tolerance for length at this particular place, and there is tolerance for height, and then there is tolerance for the angle also. Depending upon the actual sizes of this theta, length and height, this L will vary. So while giving all these tolerance values, we should see what the functional aspect of this length. So the dimensional tolerances are key in getting parts what we require, and using them appropriately will save time spent coordinating with the manufacturer and avoiding the design issues and reducing unnecessary costs. And tolerance stacking or accumulation in assemblies, they control the critical clearances and interferences in a design, such as lubrication paths or bearing mounts, and thus the performance is affected. And we should understand that tight tolerances will always increase the cost of the production, and they will also influence the selection of production processes, and then the assemblability of the final product will also be affected. So the tolerance specification, it is an important link between engineering and manufacturing departments, and to open a dialogue based on common interests and competing requirements. So far we studied about what is the tolerance and what is the fit, and why tolerances are specified, and what is the need of fit and those things. Now let us try to understand what are the systems of tolerances. There are two systems of tolerances, one is called unilateral tolerance and the other one is called bilateral tolerance. Now we can study this picture wherein we have this is the basic size of the component, basic size of the hole or basic size of the shaft, and in the case of unilateral tolerance it is specified on one side of the basic size. For example, 25 plus 0.02 mm, 25 plus 0.01 mm. Now we can see here this is the tolerance band. So this is the tolerance band, or it is also known as tolerance zone. Okay. So on one side of the basic size the tolerance is specified. This is another example. Now here there is no gap between basic size and the lower size of the part. Here there is some gap between the basic size and the lower size. For say we have a hole like this, okay, where this is the hole, and then this is the lower limit of the hole, and this becomes the upper limit of the hole, and this is the tolerance that is allowed. So the size of the hole can be anywhere between this level and this level. So it can any size it can have. Now similarly we can allocate the tolerance on the other side of the basic size. Here it is plus side of the basic size and here it is the minus side of the basic size. For example, 25 minus 0.02 to 25 minus 0.01, this is the limit of the work part. Okay. So only one side of the basic size the tolerance is allowed. Another example is 25. So this is lower limit is 25. So this is the lower or upper limit of the, if we take this as the hole, the upper size of the hole is 25, and then the tolerance is the lower limit becomes 25 minus 0.02 mm. So this is the lower size of the hole. Okay. Now what are the advantages of the unilateral tolerance system? It is easy and simple to determine the deviations, and go gauge ends can be standardized as the holes of different tolerance grades have the same lower limit and all the shafts have same upper limit. So what is this tolerance grade, we will understand after some time. And now this type of tolerance greatly assists the operator when machining of mating parts. The operator machines to the upper limit of the shaft or lower limit of the hole, knowing fully well that he still has some margin left for machining before the parts get rejected. So for example, we have a hole to be drilled, a hole is to be drilled like this. This is the lower limit of the hole and this is the upper limit of the hole. Okay. The basic size, say it is, this is the basic size which is coinciding with the lower limit basic size. Now it takes the drill tool which is corresponding to this basic size or lower limit and he starts drilling, and then there is lot of material left. So it may, the size may increase because of the vibration of the tool, the size may increase, but still the workpiece can be accepted. The reason is the upper limit is up to this, upper limit of the hole is up to this. Now the second type of tolerancing is bilateral tolerances, wherein we have this basic size and tolerance is provided on both sides of the basic size. So some examples we can see here, 25 is the basic size and the upper limit of the shaft is 25.02 mm and the lower limit of the shaft is 24.98. Now, the basic size is in between these two and the deviation is allowed. This basic size is 25 millimeter. So, the deviation is allowed on both sides of the basic size. So, that is bilateral tolerance. Now, another example is 25 plus 0.02 mm and 25 minus 0.01 mm. So, 25 mm is the basic size and then this side it can go up to 0.02 mm and on the negative side it can go up to 0.01 mm. So, this system is used in mass production when machine setting is done for the basic size. Now, let us learn about the various standards available which are related to limits, fits and tolerances. Now, we have Indian standard IS 919 and then American system ANSI B 4.1 and then ANSI B 4.2 which deals with metric units, and then we have ISO system of tolerances. So, all these standards they follow these ISO system of tolerances, and also we have American gauge design standard. Now, let us learn about some of the terminologies related to limits, fits and tolerances as per Indian standard IS 919. Now, we should understand what is the meaning of basic size. It is the size with reference to which upper and lower limits of the size are defined. It is the theoretical size of the part as suggested by the designer. So, the design engineer will make some calculations and finally, he will arrive at some size for the shaft, say 25 millimeter. So, this is the basic size as designed by the engineer. Similarly, for the hole, the engineer may arrive at some size, theoretical size. So, thus designed size is known as basic size, and then we have the terms shaft and hole. These terms are used to designate all the external and internal features of any shape and not necessarily cylindrical shapes. For example, the hole means the internal features. For example, we have a hole here. So, this feature, this is called hole. It need not be a cylindrical shape. If you have a shape like this, square hole or rectangular hole or a triangular hole, so it's that is also called a hole irrespective of the shape. It basically represents the internal features. Similarly, external features, for example, we have a cylinder like this. This external feature, diameter, outside feature is known as shaft. It can be a round shaft, or it can be a square shaft, or rectangular shaft, or a triangular shaft. All those external features are known as shafts. Now, what is the meaning of actual size? It is the size actually obtained after machining. It is found by the actual measurement. For example, so we have produced some hole by using drilling operation. See, the design size or basic size may be 25, but after producing what is the actual size. So, which is measured by using some instrument like maybe the micrometer, internal micrometer or vernier caliper. So, the actual size may be 25.02 mm. So, this is the actual size and this is the basic size, and then we have limits of the size. There are two permissible sizes for any particular dimension between which the actual size lays. So, that is maximum and minimum size, or the maximum limits and minimum limits. So, if we take the example of the shaft, so this is the shaft. Now, this shaft, the basic size say it is 25 mm as suggested by the design engineer, and he also gives some tolerance, it may be 25.01 mm, or it can go below 25 by 24.99 mm. So, this is called the upper size or maximum size of the shaft, and this is the minimum size of the shaft. And then we have tolerance. The algebraic difference between maximum and minimum limits of size is known as tolerance, and it is an absolute value. For example, in this case the difference between the maximum limit of the maximum size and minimum size is 0.02 mm. So, this is the tolerance for this particular case. Now, let us conclude the session. In this session we studied about the basics of limits, fits and tolerances, what is the meaning of tolerance, what is the meaning of fit, why the fit and tolerances are required, and what are the various types of assigning the tolerances like bilateral tolerances, unilateral tolerance, such things we studied. We will stop at this stage. In the next class we will continue the discussion. Thank you.